Welcome, everyone. My name is Mark Hughes, and I'm here on behalf of Royal Circuit Solutions in Advanced Assembly. We've got a great presentation for you. As you're probably aware, parts keep getting smaller and smaller and smaller. And once you get down to a certain size, you just can't run trace and the traces of appreciable width anymore. So what's a designer to do? Well, in that case, you need Ultra-HDI design techniques. And to learn more about them, I have a wonderful guest, Mr. Herb Snogren, who's recently added on as a consultant for Royal Circuit Solutions. So Herb, nice to meet you.
Nice meeting you.
Tell us a little bit about yourself.
Well, I've been in the industry for almost 50 years, about 40 years, I guess. Started off in high school. I started a factory in the early 80s, which is still in operation now as one of the TTM factories in Colorado. In the past probably 15 years, I've been consulting, and I've probably spent close to 8 years consulting with Royal Circuits, helping them get into HDI, and now we're moving into Ultra-HDI.
Very cool. Well, I'll have you define Ultra-HDI for me in just a minute. But for those of you who don't know, we've got two PCB factories in Southern California, one up in Hollister and another one down in Orange County near South Coast Plaza. Brand new five building facility? I forget. It's pretty big. And Herb is helping us install new equipment so we can take care of the Ultra-HDI needs. With that, Herb, man, thank you for coming on today.
Okay.
Let's get going.
All right. Let me start off with a definition of ultra high density PCBs. So these are printed circuit boards with line widths and spaces below 50 microns, which is 2 mils, Microvia diameters below 75 microns, and dielectric thicknesses below 50 microns. And these typically are manufactured with a Semi Additive process or a modified Semi Additive process, depending on the line width requirements. The modified Semi Additive process, which I'll define a little bit later, you can get down to about 20 micron line and space. And the Semi Additive process, you can use for lines and spaces below 20 microns.
So Herb, just to put this in perspective, because I don't think in microns too well, you're talking about vias that are the diameter of a human hair.
Exactly.
That's crazy.
Yep.
Can I come see this stuff?
Of course. It's hard to see with your naked eye, though.
Yeah, but I can come tour the factory.
Absolutely, yeah.
Oh, cool. All right. Sorry to interrupt. I was just excited.
So I'm going to talk a little bit about how printed circuit boards now are, the line widths and spacings and the feature sizes are being miniaturized, and what that means, why it came about, and really some of the convergence that printed circuit boards are having with integrated circuits and IC substrate technologies, because they kind of led the way in these types of geometries. So I'm going to start off with kind of a little bit of a teaser just to graphically show what's going on at these fine levels. This is a typical HDI printed circuit board. This shows an overlay of all the circuits on there. So there may be 8 circuits overlaid on there. It's got 75 micron conductors, which is a 3 mil line in space. And this is, typical HDI circuit board that we've been building in the US for, the past 20 years or so. This is a bare die from 1971. And this is the first CPU that Intel ever made, the 4004 integrated circuit. And it had 10 micron lines and spaces on it. And if you blow that up, it looks an awful lot like a circuit board, which I find kind of interesting. And I just want to show this as a graphic to show you, the comparison between a circuit board and an integrated circuit, because in many cases they're very similar. in their structure as far as the circuitry goes. So in this slide, I'm going to show how the conductor widths have evolved on IC integrated circuits, on the IC packaging substrates, and on printed circuit boards. And you see these three lines on the graph. The blue one is integrated circuits, and the feature sizes on integrated circuits. The green line is the IC substrate, packaging substrate, and the line widths on that. And then the black line is the conductor widths on printed circuit board. So if we start with the integrated circuit, back in the 60s, they were developed. They started off with, 50 micron line in space. They quickly dropped down. They were using a subtractive etched aluminum conductor in the beginning. And in the 90s, sometime they went sub-micron on their line widths, and they started using a copper-plated damascene process. And over time now, they're at 3 nanometer and 5 nanometer nodes now on advanced IC substrates, and I think the line widths on those are in the 30 or 40 nanometer widths. So
that's
very,
insane.
very, very fine, yeah.
You can start counting atoms, across at that point.
Yeah, once they get into sub nanometer, then you're getting into atomic level. So it's they're going to reach their limit at some point.
Yeah.
So as ICs developed, they were packaged using lead frames, and so these were etched or stamped lead frames, and the bare die was wire bonded to that, and then the IOs came out to these pins that were either through hole mounted on the circuit board or surface mounted. But as the density and IO density of the die increased, we couldn't put enough pins around the perimeter of the package, to be able to connect to the circuit board. So we had to go to a grid array packaging, and that happened sometime in the late 90s. And if you were building circuit boards in the late 90s, early 2000s, all of a sudden you saw these printed circuit boards with ball grid array patterns on them. And that BGA packaging spawned an industry building these IC substrates, which are like tiny little circuit boards that served as an interposer between the die and the circuit board. And, again, that happened in the late 90s. The line width and space on that packaging substrate started off around 50 microns, and they were using a subtractive etch process and Microvias at the time. Then they went to the modified semi-additive process, and they were getting down to 20, 25 microns. And the advanced IC packaging today, which goes down to probably around 6 micron lines and spaces, uses a semi-additive process currently. So on printed circuit boards, we started off with a subtractive etch, and the first circuit boards back in the 50s were probably 50 mil, 30 mil lines and spaces. As the component density increased, we had to decrease the line widths, and so there was a continuous decrease in line widths. In the late 90s, when we introduced these BGA patterns, we had to use HDI technology on the printed circuit board. So that was using finer lines, Microvias for routing. And, we kind of leveled off at a 3 mil line in space or a 75 micron line in space. So the industry as a whole for 10 or 15 years was kind of stuck at this 75 micron line width and space limit. But in the past 10 years or so, especially in consumer electronics coming out of Asia, line widths were dropping, below 75 microns. In Asia currently, on a lot of handheld products, there's products out there for cell phones and watches and in-ear devices that are using the mSAP process, the modified semi-additive process. And these circuit boards have 20, 25, 30 micron lines and spaces. In the future, go ahead.
Oh, no, no, no. I was just going to say that is amazing.
Yeah, it's pretty phenomenal at what's happened in the last 5 or 10 years in the circuit board industry. And again, mostly in Asia. In the future, semi additive process and maybe some sort of fully additive process will be a future enabler to get down below 20 micron lines and spaces on printed circuit boards. So that is the trend. It's going to get smaller and smaller and smaller. But what you can see in this graph is that printed circuit boards have entered into an area on feature sizes that, in the past has really been the domain of ICs and IC substrates. So, this has happened in the last 5 or 10 years. So fairly phenomenal and interesting things happening in the industry. Again, mostly in Asia at this point in time.
Hey, Herb, one announcement and one question for you.
Yeah.
The first announcement is for users or participants watching this, please ask in the Q&A. If you ask in the chat, it scrolls and I'll lose your question. But if you ask in the Q&A, I can keep track of it. So as we go through and you have questions, if they're appropriate, I'll insert them then. If not, I'll hold them till the end. Now, my question for you, Herb, is, well, why is everything getting so small, man? Why are the IC manufacturers pushing to 5 and 3 nanometer nodes? Why do we need them that small?
Well, the 3 and 5 nanometer nodes are on the IC, and that's just to stuff more transistors into an area on the chip, on the silicon. So, but again, they're getting to the limit on that. And so we're coming up with different packaging techniques with heterogeneous packaging, which I'll talk about a little later, which is going to drive, the line widths and spaces on printed circuit boards. So I will talk about some of that in future slides. So I talked a little bit about these IC packaging substrates, and they're like tiny little circuit boards that provide like an interposer between the die and the printed circuit board. And they really spread out the IO pitch from the die to something that is suitable for a printed circuit board. So you don't have to build a printed circuit board with 6 micron lines and spaces. You can do it with 50 or more lines and spaces. So typically these are multi-layer organic substrates. They're using Microvia technology for interconnects, and their line width and spaces are between 6 and 25 microns. Although that, the roadmap on that is probably getting down towards 2 micron line and spaces in the future. Typically, they're using BT and Ajinomoto buildup film as dielectrics. So a little bit different than circuit boards. They're currently being manufactured either with the modified semi-additive process or with semi-additive processing using either electroless copper or vacuum deposition. So I show this just to show you, that industry has been around for quite a while, and they're kind of leading the way for printed circuit boards. So we're kind of following in their path. And that's why there's a new type of printed circuit board terminology out there that we call substrate-like PCBs or SLPs. And these are printed circuit boards that now are using features that were previously used on IC substrates. So they're, typically have lines and spaces below 30 microns, smaller via diameters, sub 75 microns, via diameters, and dielectric thicknesses that are below 50 microns. And, right now in Asia, these are being manufactured with the modified semi-additive process. So how did this all come about? Why did ultra-HDI PCBs become so commercialized? And we can really blame Apple for that. They wanted to pack more power into their device and keep it small. So they pushed their suppliers in Asia to start developing processes that would allow them to use finer pitched devices on their motherboards. And so, they went below 50 microns on the iPhone 6 and 7 using a subtractive process. And then when they got to iPhone 8 and beyond, then they started using the mSAP process on some of their routing layers to get down to 30 micron lines and spaces. And as a result of that, and just that capability in these HDI factories in Asia, other industries or other end use products were able to use that technology as well. So you've got, earbuds, that are using little circuit boards that have 25 and 30 micron lines and spaces. There's implantable medical devices. Your Apple Watch has got a 20 or 25 micron line and space printed circuit board in it. So there's a lot of consumer and medical electronics now that are using these ultra-HDI PCBs. But Apple really kind of spawned that in the industry with the iPhone.
Hey, Herb, we've got a question that may be relevant to the size question, or the size that you're talking about now. Hamid wants to know the difference between CSP and BGA, so chip size package and bulk array.
So a chip scale package is typically they're going to do that with a wafer level packaging. And so the actual package size is the same size as the die. And so what they do is through wafer level packaging, they add dielectric layers and circuit layers onto the wafer. And then they terminate out to their bump or the ball, and then they cut that out of the wafer. And so it's the same size as the die. Whereas using a organic substrate, the substrate is bigger than the die, and so it's a separate component. So the die is actually placed on the substrate, whereas with chip scale packaging, the circuitry or the fan out circuitry or fan in is built up on the die itself. I believe that's correct.
It makes sense to me. Thanks, Herb.
Okay. So, here's the drivers for Ultra HDI PCBs. It's, primarily product miniaturization. So you're putting, higher powered components on a smaller and smaller motherboard or platform. And you have to have finer lines to be able to do that. The components, particularly the BGA components, end up having higher IO densities. So the pitch goes down below 0.4 millimeters. And once you get below 0.4 millimeter pitch, you've got to get into these sub 50 micron lines and spaces to be able to route those out on the printed circuit board. Heterogeneous integration, which is a whole topic in itself, but that is going to lead towards much higher IO densities on the component package. And so you're going to have much finer pitch, larger devices, and that's going to drive, the routing density on the printed circuit board to use finer lines as well. Some of the high-speed designs that are coming out now that are going, above 25 gigs, they're going to require much tighter line width tolerances and much more controlled conductor geometries for signal integrity. So you can get some of that using the modified semi-additive process or semi-additive process. You just can't get there with the subtractive process. And I'll show some examples of that in an upcoming slide. And then there's going to be some RF designs that have elements that are going to require some really fine features with very, very fine line widths and spaces. And those are going to be below 50 microns as well.
That actually answers it almost answers another question. So if you've got an engineer who needs this Ultra HDI and also wants to incorporate, say, a millimeter wave circulator or other millimeter wave structures, we can do that.
Probably. I'm not an electrical engineer, so I probably can't answer those kind of questions.
Okay. But well, Ben asked, my friend Ben Jordan. So Ben, I'm going to say yes.
but it's probably the case, yes.
I'm going to say yes, and then if we can't do it, you heard it from Herb first, and he's a dirty liar. All right, cool.
So here's another benefit of using UltraHDI layers in a design, and this came from a presentation that we had at APEX, corresponding to the one that I made, and this was from Meadville in Asia, who is an HDI manufacturer for Apple and others. And they presented this slide just showing some of the benefits of using HDI technology and line widths. And here you've got a fairly large IO 0.35 millimeter pitch device. And these are different ways you can route it out with different line widths. So, in option A, using a 40 micron line width and fairly large pads, you can only run one conductor between pads. If we can go down to a 35 micron line, we can run two conductors between pads, and we can reduce the layer count down from 18 to 14 to get that routed out. And then if we can go down to even a finer line width, down to a 0.3 or a 30 micron line width, we can route three conductors in that channel and go down to 10 layers. So you can reduce the layer count by 8 layers, which reduces the thickness of the board, reduces the number of lamination cycles by 4, the number of drill cycles, by 4 or 8. So the cost of the product would go down considerably just by reducing the layer count. So that's one big benefit of employing UltraHDI layers for routing some of these BGA devices.
How many lamination cycles can you do with this technology?
Well, we're seeing a lot of stuff with 4 and 5 lamination cycles. So, 4 stack Microvias. It's fairly typical.
Okay. And that answers Eric's question. So 4 and 5 layer or lamination cycles. When you make these layers, is this, I guess it's, and I apologize if this is a stupid question, I'm just not familiar with the technology, but are we doing cap or foil, sequential construction on these things?
It'll be sequential. So it's a build-up process. And this next slide shows kind of how that circuit formation process works. So what I show here is kind of the progression of conventional pattern plate on the top. Typically, we can use that to get down to 50 micron lines and spaces. And we start off with, a copper clad laminate or a multi-layer structure with copper foil on the outside. And that can go down to, say, 9 micron thickness. But, on typical circuit boards, we're using 1/2 ounce copper or 1 ounce copper. Then we'll drill holes, go through electroless copper, and then we image it with dry film, and then electroplate copper and tin. Then we strip the resist and we etch. And that leaves the circuit conductors, and they've got kind of a funny shape to them because of the plating and etching process. Kind of the next level down, and this is what is used a lot in Asia on cell phone boards, historically, is a panel plate subtractive. And for that, typically you can go down to about a 40 micron line in space. Again, they'll start with a laminated structure with copper foil on the outside, typically thin copper foil, 3 to 9 microns. They'll drill holes and then electroless copper plate that, then go through a panel plating process to where they plate the whole surface with electrolytic copper. Then they'll image and etch resist and do a print and etch, and then strip the resist. To get down below that 40 microns, the next process technique would be to use the modified semi additive process. It's similar to the pattern plate process, except we're using a very thin copper foil to start with. And with this, we can get down to 20 or 25 micron line of spaces. So here we start with a laminated core or inner layer, and it has 3 to 5 microns copper foil on it. We'll go through a drill and electroless copper plate, and then image it, electroplate the copper. We don't need to plate tin because what we're etching off is so thin. So we just strip the resist and we go through what's called a differential etch. And we just etch that background copper off, which is, fairly thin, 4 or 5 microns. And then we leave the conductors. And you can see the conductors in this process kind of retain their square shape. They don't get trapezoidal or curved like they do in the panel plate or pattern plate, conventional pattern plate. If we want to go to a even finer feature size, then we can use a Semi Additive process. And this starts with a laminated structure with no copper foil. And so we have to add a seed layer to that. We can either do that with electroless copper, or we can do that with vacuum deposited copper. The vacuum deposited copper is much thinner, so you can even do finer lines with the vacuum deposited copper. So we'll put that seed layer down. Then we go to image it, electroplate. We strip the resist, and then we do that same differential etch where we remove that seed layer. And because it's so thin, it really doesn't even touch the conductors, so they remain almost intact. And so you get a very square, uniform conductor at the end.
What about aspect ratios?
So you do have what's called an imaging and a plating and etching aspect ratio. The main one is really the imaging aspect ratio. So typically what you see when the line widths decrease, we have to use the thinner resist to be able to resolve those line widths. So most people, when they start getting into line widths and spaces under 25 microns, they're using 25 micron resist or 25 micron resist. They even make 12 micron resist and 8 micron resist when you get down to the 10 and 6 micron lines and spaces. And that's just to give you a reasonable aspect ratio for imaging and developing and plating and etching. And so that limits the plating thickness as well, which I'll talk about a little bit later. So is that the aspect ratio you were talking about, or was it more of a whole aspect ratio?
No, that was the aspect ratio I was talking about.
Okay. Yep.
And again, for participants, please ask your questions in the Q&A. In the chat, it's very difficult for me to see them and keep track of them. We do have some other questions, but you can take them now or take them later. It's up to you. What would you prefer?
Yeah, how much time do we have? Yeah, I could probably take a few now.
Okay, yeah, we've got 30 minutes.
Okay.
Okay, so let's do some low-hanging fruit. What IPC classes are possible?
Let me talk about that in a later slide.
Okay, we'll hold that one.
Okay.
When will Royal have this capability up and running?
I have another slide for that one too.
Tell you what, let me hold the questions. Let's just move through, and then if I get any specific to a slide, I'll stop you there. Okay.
Okay. Yeah. So again, back to the aspect ratio, we typically look at that as 1:1. So the thickness of the resist would be equal to the maximum width that we could, or the minimum width that we could resolve. So if we use a 25 micron resist, we can do a 25 micron wide conductor or more. So these are the things that enable us now to be able to do this ultra-HDI technology. And a lot of this wasn't available 10 years ago. So especially to the printed circuit board industry. Probably the key one is the high resolution direct imaging. There's direct imagers out there now that go down to 2 micron feature sizes. It just wasn't available in our industry 5-10 years ago. And then the high resolution photoresists, these are fairly new to the industry. Along with that, the high resolution AOI. So, if you can image it, you need to be able to inspect it. So we need automatic optical inspection equipment that can do these fine lines. Also, in order to do the semi-additive or modified semi-additive process, we have to be able to fill the microvias and plate the conductors simultaneously. And over the past 5 or so years, plating chemistries and systems have been developed to be able to do that. The other one is the ultra thin copper foils. Now you can buy commercially copper foils that are 1.5 micron to 3 microns thick. These weren't available years ago, and what companies were doing was etching down 1/2 ounce copper or 1/8 ounce copper to thinner foil thicknesses. And now you don't have to do that. You can just buy some off the shelf thin copper. In order to get into semi-additive process, there is chemistry out there that act as adhesion promoters or activators to allow the electroless copper or vacuum deposited copper to stick to the laminates. In America, commercially, Veritex got their ASAP process, and Additive Circuit Technologies has got their proprietary process that's kind of similar to that. So that allows you to get into that semi-additive process with electroless copper. So if you're a typical printed circuit board shop, some of the things that you would have to do to go from being able to do, conventional HDI to Ultra HDI, you'd have to employ a, semi-additive processing, so be able to, deal with the thin copper foil, or you'd go to a semi-additive process using something like a Veritech or Advanced Circuit Technologies process. Cleanliness is going to be key. Little particulates either in the air or even in the chemistry, which doesn't pose a problem, or you can't even notice it when you're doing 75 micron lines and spaces, suddenly became a big problem. So, cleanliness is going to be critical. Tight process control within the shop is going to be mandatory. We're going to have better thin material handling. A lot of these boards are going to be very thin. They're going to start off with a 2 or 3 mil core that we have to drill and plate. Wow. And then build up from there. So
how do you do that? Do you put them on carrier sheets or?
Yeah, you can do carriers. A lot of the equipment that normally was maybe in racks and horizontal dipping has to go to horizontal processing. Either that or you have to frame it for handling if you want to go vertical. So, and handling, just these features are so small that it's very easy to damage them. So the handling is really critical. Laser drilling with small diameter capabilities. Again, we talked a little bit about the resist. If you want to go under 25 micron line and spaces, you've got to use thinner resist to be able to resolve those. So the resists are going to be thinner. And then that high resolution direct imaging that we talked about. Then the specialized plating, being able to fill the microvias and plate the conductors simultaneously. Also something with very good plating distribution, because we are using thinner resists. We have to have very good distribution in plating, otherwise we're going to plate over the resist and have etching problems. And that gets a little bit into the design too. The designs have to be designed where they've got even distribution of copper across the board in the panel. We have to have a differential etching process. When we get into mSAP and SAP, we're etching, 1 micron to 4 microns of copper, as opposed to say, 30 microns or 20 microns. And so the conventional etchers that we're using, you can't run them fast enough to be able to etch that thin copper. So we have to get a different etcher in that etches a lot slower, and we can run it through at a reasonable speed to be able to etch that background copper off without an etch resist. Again, the AOI with fine resolution. Another thing that people don't think about, but controlled solder mask thickness is going to be critical too, especially if on some of these ultra-HDI boards with fine pitch, the assembler is using a gel flux process rather than using paste. You don't want the solder mask so thick that it creates a standoff, and the bumps don't contact the pad on the printed circuit board. And then electrical test capabilities of probing down to these finer pitch features on the printed circuit boards.
That's, just the amount of device setup and certification, required for all of those things. I can't even imagine those poor process engineers.
Yeah, there's a lot of development and it's a lot of process control. In Asia, the companies that build these products, that's all they build. So, they don't build a wide range of printed circuit boards. They focus on just a specific type of HDI. If you go into a substrate manufacturer, they just make substrates. They don't make circuit boards. And so they really control their processes down to a T. So someone asked about the development at Royal. We're working on it now. We just started early this year. So we're in what I call the phase one, and we want to be able to establish 40 to 50 micron line width and space capabilities for production. We've got some of the equipment to do that with the direct imaging and AOI equipment. We're just finishing up now the resist evaluation, which I did a couple of weeks ago. And I was surprised actually that we were able to resolve 1 mil line in space, so 25 micron line in space. And so here's some pictures here of the test pattern that we used. And then this is a cross section of the conductors that were plated. We didn't get to etch it because I haven't evaluated the foil yet. So we just imaged it and plated it. And so you can see that we got, on our first shot with this particular resist, we were able to resolve a 1 mil line in space.
Wow.
So our next step over the next couple of weeks is to laminate some structures with the 3 micron foil, plate, and then etch this same pattern. And so we should have that done in a couple of weeks. So, we're well on our way to, finishing up phase one, probably by summer. I'm thinking we have a couple pieces of equipment on order. They're really going to be the pasting items to get the differential etcher and the via fill process in place.
So one thing I will say, because that question was asked by Bill, we apparently had to no bid a design for him because we couldn't do it. One thing I will say, Bill, sorry about that. We're still waiting on equipment, but we still offer free engineering services. So if you have questions, come to us. Even if you can't be our customer right now, maybe you can next year. So we're happy to help. Send your questions. We'll try to get them directed to the right person. Whether that's Matt or Herb or John or Elijah or whoever the right person is, send us your questions. We'll try to help you out that way. Okay. It's no charge for that.
So our phase two is to establish the 25 to 35 micron line and space capabilities. I think we're going to, based on the testing we had on the resist recently, which surprised me, I think we're going to be probably pretty far along with this towards the end of this year. Our direct imaging equipment can do it now. We can easily upgrade our AOI equipment in the plant without buying new equipment. So I would guess by sometime fall, late fall or winter, we should be able to start doing some 25 to 35 micron line and space work in production. So we're talking a little bit about, somebody asked about specs. So the IPC standards if you go into 6012, 6013, or the design standards, the 2220 series, they really kind of stop at 50 micron lines and spaces. And so that gets you down to a 0.4 millimeter pitch device. If you go down below 0.4 millimeter pitch, the IPC standards don't really apply very well to that. And so, you know, this is out of IPC 2226, which is the design standards for HDI printed circuit boards. And they divide producibility categories in A, B, and C. And so level C is the highest, or the highest category, the lowest producibility. And that you can see here in this column, it stops at 50 micron lines and spaces. And so they really don't have any design guidelines or standards in there for going below 50 micron lines and spaces, or using thinner foils or no foil. So in the design standards, you know, there's a hole. So we need to get some standards put together for ultra-HDI. So I've added this other column here, and we are working on this. I'm chairman of a committee for the IPC, and we're working on developing some design standards for ultra-HDI structures. On the printed circuit board side of things, on the end product, you know, there's the IPC 6012, 6013, that whole series. Again, a lot of the requirements in there, whether it be class 1, 2, or 3, really aren't very suitable for ultra-HDI technology. So, you know, conductor thickness is an obvious one. You know, as you go down to feature sizes that are 20, 25 microns, you know, people aren't plating those up to, you know, a mil thickness typically. You know, they're more at 12 to 18 microns on most boards. So there's a different standard required, I think, for the ultra-HDI conductor thickness. Same with the plated through hole thickness. IPC really doesn't deal with thinner copper foils than 9 microns, so we need to rewrite the standards to, you know, apply to thinner copper foils or no foil if we're using the Semi Additive process. You know, the laminate defect allowances, a lot of those are just absolute numbers, and you know, they work fine when you got 3 mil lines and spaces. They don't work really well when the line widths and spaces are below 1 mil. Whoops. So there's a lot of criteria in the standards that need to be updated for ultra-HDI. Which brings me to the IPC D33AP committee. We established that a little over a year ago, and we are trying to develop design guidelines for ultra-HDI structures and also product performance and quality standards for ultra-HDI structures. And we want to make sure that the design guideline is consistent with the end product specifications, because in a lot of cases right now, you know, we find that the design standards aren't always consistent with the product specifications. And we found that with the, I think the medical addendum, which tries to deal with some of these fine features, and it's just inconsistent with some of the other standards. So from an ultra-HDI design, and for anybody out there that wants to implement this in their product, they really need to work hand in hand with their manufacturer. So everybody's manufacturing process is going to be a little different. They're going to have different capabilities. They're going to set their process up around some fairly strict standards on what they can do and what they can't do. And so you really need to work closely with your fabricator on designing around their process. And this is, again, more IC fab-like than it is traditional printed circuit board design, like, which, you design something and get somebody to build it and they figure out how to do it. In IC fabs, they have their design standards. They give that to the designer and they have to use those standards if they want to design for that foundry. So that collaboration with the fabricator is really critical. And there's going to be a difference. If somebody's using subtractive, they're going to have a different capability than somebody that's using mSAP. Somebody with mSAP is going to have different capabilities than somebody using Semi Additive Process. And even within those, depending on their equipment platform, they're going to have different capabilities. So again, you just have to work with your fabricator there. The other thing to be aware of is that most of these designs are going to be hybrid. They're not all going to be ultra-HDI on every single layer. So, on a cell phone circuit board, for instance, there are layers that are made with subtractive etch, and then they do buildup layers with ultra-HDI, and then they finish up, with a subtractive layer for the outer layer when they have through holes. And so you're going to have different design standards and end product criteria that apply to those layers differently. And so you need to be aware of that when you're designing the board and also evaluating that. So there can't be just a single, global standard for the entire structure. It's got to be, different layers are going to have to be treated differently.
Oh gosh, that's going to be a lot to set up in your design rules.
Yeah, exactly. So, you're going to have design rules for ultra HDI layers and design rules for subtractive layers. So they'll be different.
Well, like you said, it's going to have to be getting to know your fabricator. And if you use multiple fabricators, you're going to need different design rules for each one of them. Man.
Yeah, that is possible. I mean, that's what happens at the IC foundry level.
If anybody's listening out there and you want to start a website that does that, I would gladly pay you $5 to import design rules than make my own. Wow.
There will probably be a lot of commonality, generally between different companies. So it probably won't be as, critical as it is with, doing substrates or even substrate or ICs themselves. But we're moving closer to that side of things where the fabricator is going to really dictate what the end product's going to look like, and you're going to have to design around those standards.
Yeah. Wow. All right.
So that kind of brings me to the end. So I guess we can open it up to some questions.
Well, we have some questions. Let me tell you, sir.
All right.
And fortunately, we have some industry experts in our audience that can help answer them. The first one is going to be for Mr. Chris Hunrath of Inselectro. Chris Hunrath has been a frequent guest of our, by the way, Chris has joined us in the Just So You Know, Herb. But Chris Hunrath has been a frequent contributor to these webinars. He's a font of information, a walking encyclopedia of material science knowledge. So for that, I want to give the question from Greg to you, Chris. What is the copper surface finish roughness of these processes? He's concerned about, high gigahertz, 25 gigahertz signals.
Sure. Yeah. Could you hear me all right?
Yeah, we can hear you just great, Chris.
Great. Yeah. So, I mean, obviously that's been a hot topic in the last couple of years, is the copper foil treatment roughness. Now, the treatment there is there to enhance adhesion, which is very important. And as Herb mentioned, some of the electrolysis processes have been enhanced with special activation systems to get that adhesion. But on the thin foils that are typically bonded to a peelable carrier, the treatment on them is just above 1 micron. Now that might seem thick for 1.5 micron foil, but the treatment's added on top of the 1.5 micron foil thickness. So it's a post process where the copper nodules are plated, and then there's some chemical treatments added on top of that. But it's about 1 to 1.25 micron for the 1.5. You might get as high as 1.5 microns on the 3 micron foil, but it's very smooth, compared to standard foil. Standard foils, half ounce might have a six or even 7 micron treatment. VLP, is in the 4s, and then the HVLPs, and is around 2 to 3 microns. So it's very smooth by standard foil standards.
Do we have any problems with spontaneous delamination because it's so smooth?
That is a concern. It won't spontaneously delaminate, but certainly if you're bonding components to it, you have to be aware of the fact you're not going to have the same adhesion as you would with 6 micron foil. You just don't have the surface area to get that adhesion. That said, the chemical bonding treatments and some of the modern laminates stick pretty well to the foil. So from a thermal performance standpoint, that's a complex issue. Everything from the CTE of the resin system to how well it sticks to the foil. But certainly if you're bonding components, larger components to it, that could be a concern, but honestly, I haven't seen a ton of issues with that.
All right, and then I have another question that you might be able to answer from Greg. What types of flexible dielectrics are possible with this process?
The flexible dielectrics, well, really anything you can laminate the thin foil to. The flex materials are pretty much limited to 5 micron foils and thicker. There are some specialty flex materials that are sputtered and then plated. But if you have high temperature lamination capability, you could use what's known as a TPI layer to bond the ultra thin foils to, or you can use something like one of the new epoxy adhesives, and that stay flexible, and use that as an intermediate. That's a whole nother topic, and Herb, you might want to have a separate webinar on ultra thin dielectrics.
Yeah.
But there are new materials emerging all the time. So, if you would like to collaborate on that, I'd be happy to provide you with some of the information on some of the new products.
If I could offer, gentlemen, PCB West, the submissions for abstracts closes tomorrow. That would be a great one.
Indeed.
If you're interested, I can type it up for you and get it submitted. Does that sound like something you both would like to do together?
Sure. Yeah, let's talk offline about that. But yeah,
Okay.
There are some new materials that have just come out that might have application for this.
Okay, perfect. So Chris, thank you so much. I think we can let you go now, but please stay on if you have time, but if not, and you need to bounce, that's why I asked your questions first.
All right, appreciate it.
Sure. All right. Herb, you ready for the speed round?
Sure.
Okay. So one question is, any data about reflow reliability per IPC 2.6.27?
I don't have any. I mean, there's a lot of data out there. There's a IPC committee that's studying Microvia reliability. So it's probably best to get data from them. And I know at APEX, they had several presentations. I personally don't have any, but there is a lot of data out there.
And there's companies that do the testing, independent testing companies. You might even want to just call or email one of them and find out what they're seeing, come into their shops.
Yeah.
What is the typical delta in cost between a conventional PCB with 3 mil trace space versus an ultra high density PCB with 1 mil trace in space?
That gets kind of complicated because, as we looked at that example with that BGA pattern and the different routing with different line widths, if you're using these finer lines to reduce layer count, it could be a trade-off to where there's not a lot of extra cost. If you're going from an 8-layer board with 3 mil lines and spaces to an 8-layer board with 1 mil lines and spaces, it's going to be more expensive. But if you're able to redesign an 8-layer board with 3 mil lines and spaces to a 4-layer board with 30 micron lines and spaces, and it's a smaller board, less layers, it may not be that much more expensive.
What about NREs, non-recurring engineering fees for this type of thing?
You know, historically, Royal hasn't charged NREs. So other companies do. I don't know what, the difference would be. I don't, it doesn't really make that much difference in the tooling aspect. It all looks the same, in the CAM system and the creating the travelers and things like that. So I don't think there's going to be really a difference on the NREs, between this.
Okay, thank you. William would like to know, are there any resources to calculate current carrying capability of these Ultra-HDI traces? Will conventional calculators be accurate in this range? And I can take this one if you can't, Herb.
Yeah, IPC has some conductor width calculators, and it's based on temperature rise. Actually, a friend of mine developed those. He lives pretty close to me. I don't know. I talked to him a few months ago on their application to these fine lines, and I think they would work. But I'm not 100% positive. So that maybe if you've got an answer for that, then
sure, I can jump in there. Or were you talking about Douglas Brooks at all, or
no?
A different friend?
Mike Jopi.
Okay. So let me jump in, because this could be a whole topic by itself too. A lot of the online calculators, and fortunately they're changing now because I've been stomping my feet, are using an outdated IPC 2221 equations. Those were pretty much just made up by a couple guys in the 1950s, 1960s, and somehow became canon. They're complete BS. So IPC 221, is, as far as current carrying capabilities, has been supplanted by IPC 2152. And even then, if you look at the numbers there, all of the tests are for a single copper trace, in the absence of anything else, which means that they're going to be a little more conservative than you necessarily need if you've got, 2 mil dielectric and a copper plane underneath it. That's going to be what's carrying your heat away. So if you do use an online calculator, make sure that they've updated IPC 2221. Now, as far as other good resources, if you go to ultracad.com, Douglas Brooks and Johannes Adams have some articles there. Actually, Dr. Brooks just wrote a whole book on it that he released, I don't know, 6 months ago, something like that. That'll walk you through a lot of the information that you need to know. They did modify the equations ever so slightly. And if you want to shoot me an email, I'd be happy to type all that up for you. And maybe give you a little more information, but I hope that answers it. I kind of feel like I talk too much, but I don't know. So, all right, we've got a few more, and please feel free to keep asking them. I don't know if I understand this one, but it says, is it possible to combine these Ultra-HDI processes with additional special materials such as RF ferrites?
I don't know what an RF ferrite is, so does Chris Hunrath know if he's still on?
He's muted. He might have wandered. Okay, so I know what RF ferrites are. I don't know what they are in context of this question. So a ferrite is basically you run a wire through a material with a high permeability, and you can capture RF noise and keep it from wandering out. Maybe they're talking about depositing that material on the board. I'm not sure. Mm-hmm. So, and that person wandered away because they have a dentist appointment, so I can't follow up. But Ben, you know how to contact me. In fact, we talk like 3 times a week. So ask me and help me understand the question, and I'll get an answer for you. Keith would like to know if there are any additional constraints on assembly tolerances, like pick and place, to utilize Ultra-HDI enabled package pitch that we're discussing here.
Yeah, I think so. So, when you're starting to assemble BGA packages that are, below 0.3 millimeter pitch, you're starting to get into the IC packaging placement equipment. And so, it's similar types of placement accuracies that you're going to need there. So you may have to have equipment that, has a 30 micron or less placement accuracy for these real fine pitch components. But I think that's, you have to get down well below the 0.3 millimeter pitch devices to do that. But, as that pitch goes down, you're going to have much, more precise placement, component placement, and also more precise solder paste capabilities, et cetera.
Yeah, and usually when you're down that small, you're going to have to put fiducials for these components. I forget the exact standard. I want to say it's 7351, but I don't think that's the right standard. Yeah, that's not the right standard. But you still have to look at your least, nominal, and most courtyard placement capabilities. You want to give your assembler enough space to get in there and move things around if they need to. And if you're using the least land pattern protrusion standard, so everything, the courtyards are all really, really tight. If something goes wrong, nobody can do anything about it. Things are just too close.
Yeah.
So talk to your assembler and see what's capable. Ask them where they think errors in placement might occur and try to give them a little more space around it. So, if it goes through X-ray and they see that it doesn't fit, they can get in there and reflow it and, fix it. Otherwise your yield's going to drop. So hope that helps, Keith. Will a copy of this presentation be made available? We hope so.
Yeah, I think so.
Yeah, we'll probably put it at royalcircuits.com/blog. Is usually where we put the presentations and the videos when we get them. So we believe so. We did the delta in price. Keep asking questions because we are almost out of them. So if you do have a question, ask it now, because once I finish this list, we are done. You mentioned that this technology is already being used. Have there been any issues reported from the field?
Well, it's been used for years in Asia because the circuit board in your iPhone or your Samsung phone, is using this technology now. So I think in those devices, the reliability has been pretty good. But in the US, we haven't really developed this technology yet to get a lot of experience. But the experience in Asia, I believe, is good. Certainly on IC substrates, they've been doing it for over 10 years. On cell phone boards, last 4 or 5 years, they've been using it, and it's been very effective and I think pretty reliable.
All right. Mark asks, how is fully additive process different from semi additive?
Yeah, that's a good question because there's a lot of debate on the terminologies. And I know there's an article recently, I think interviewing some of the folks at Calumet, and they had a pretty good take on it. Technically fully additive means you're only adding material to something and you're not taking material away. So, that would be like 3D printing conductors and 3D printing dielectrics and things like that. So you're only adding things. So that would technically be, an additive type process. But I think semi-additive kind of falls into that because that seed layer that we're adding is so thin that when we take it off, it's pretty irrelevant. So I think in a lot of cases, Calumet, says we kind of consider semi-additive process an additive process. But technically additive means you're only adding and not taking anything away, where semi-additive means you're taking a little bit away in the etching process, whereas a subtractive process, you're subtracting a lot of copper to form the conductor. I don't know if that answers it, but
I think so, but Mark, you've got probably 60 seconds to ask again if it didn't. Amba asks, are EDA tools available for Ultra-HDI? I think I can answer that one if you can't.
They are. I mean, there's really not much difference between an HDI design and an Ultra HDI design, except the feature sizes. So I believe they're there.
Yeah, I was going to say the same thing. Your pretty much any EDA tool, even the free ones, should be able to do this. It really comes down to having different design rules more than anything else. But, you know, Altium, Cadence, you know, you get down to the, let's call them more introductory ones, Dip Trace, even KiCad or KiCad, I still don't know how to pronounce that, should all be able to do this. But what's different is when you start running your DRCs, you're going to have different things set up. And as Herb said, you might not want Ultra HDI on every layer. So that means you need different DRCs for each layer. Now, that's where things could get a little tricky. I don't know the EDA tools individually well enough to know if, you know, if they all can do that, if they can separate out layer rules. I'm 95% certain Cadence and Altium can. But if we're talking the more introductory stuff, the Dip Trace, the KiCad, I'm not too sure if they have different layer rules for DRC, which means then that on your non-Ultra HDI layers, you're either going to be throwing errors left and right, or you know, or the other way around. You know, your Ultra HDI layer is going to be throwing errors left and right. So I don't know. So, all right. With that, Herb, man, that was a lot of information. That was great.
Yeah, we got it done in an hour, so not too bad.
Not too bad at all, man. I really appreciate your time.
All right.
So before we go, just a couple quick announcements. If you enjoyed this webinar, if you enjoyed talking to Herb, let us know. We try to do these and do webinars that interest our customers. So if you have something that you want to know more about, let us know and we'll put it together. Every Friday at noon Pacific, I destroy something and we look at the technology inside. It's called Mark Voids a Warranty, and it's on Advanced Assembly's YouTube channel. We just blew past 600 subscribers. A week ago, we were at 494. Now we're at like 640. It went crazy, but that means I get to start taking apart expensive stuff. Yeah. So Google Mark Voids a Warranty and come check it out. There's more news. Royal next month will be hosting a design competition with $500 in prizes. We're going to be giving away $150 gift certificates to Adafruit. We're going to be giving away soldering irons, the pine soles. We're going to be giving away all sorts of stuff. It's a really cool project. It shouldn't take you much time to design it. What we're really looking for is creativity. But your BOM count is going to be like 10 items, 2 unique items, a microcontroller and some RGB LEDs. But the way that you put them together, that's what's going to be key. So keep an eye out for that. You'll definitely see it show up in your news feeds. You can find us on LinkedIn, on Facebook, on YouTube. YouTube's the best. I think we have a Twitter even. I don't know. I don't tweet, but there's ways for you guys to get back in touch with us and let us know what's going on. We will post this at royalcircuits.com/blog. And with that, Herb, thank you so much.
All right. Thank you. Enjoyed it.
All right, everyone. Have a great rest of your day. Bye.